So we'll go ahead and get started and I'll introduce us. So thank you for being here. This is Topic Modeling with Jupyter Notebooks. I'm David Closter, and then my colleague Katie Chapman will be presenting this. We are with Cyberinfrastructure for Digital Humanities and Creative Activities, CyberDH for short. That is part of Research Technologies, which is part of UITS, which is all here at Indiana University. So lots of umbrellas and they all get smaller. And we are having an issue. There we go. Okay. Apparently I wasn't hitting the key hard enough or something. So if you want to follow along, you need to have a Carbonate account. I know at least 2 of you should have yours already since we had an issue last week with it. To figure out how to do that, there's a link here, the first one. It'll go to the knowledge base and show you steps on how to do that. Usually takes about 20 minutes or an hour and a half in some cases. So you might want to do that now if you have not. If you want to access today's slides, that's the link at the bottom. You can have them then for as we go through it, or if you just want to have them for later. Yeah, it's a new set. It's a new set because it's a new topic. So yeah, it's a different link to a different set of slides. You will see some similar slides in there, but. So our schedule, again, if you missed last week, we have the link to last week's slides right here. So if you want to go back and grab those and you can go through it. Today, again, topic next week is sentiment analysis. Same time, same place. Yeah. Mm-hmm. Okay. Another technical difficulty. Hold on. All right. Is everybody good? Okay. Thank you, Katie. Okay. And then there's that link. Does anybody need that still? For the old ones? No? Okay. All right. So don't be fooled by the short outline. This is going to be fairly long, and so I might talk very fast. If you have questions, try and save them to the end if you can. If it's really important that you interject, that's fine too. But you're probably going to notice we're going to go through this quickly because we're going to have a lot to say. So to pregame, same as last week, you can access Research Desktop either via ThinLink client, or what we're going to do again today is just access it via red.uits.iu.edu in your browser. It does use the supercomputer Carbonate. That's why you need a Carbonate account. So if you don't have that account, you'll get to this link and it will not work for you. The other really nice thing about why we're using Research Desktop is our notebooks installed, so you don't have to install it. So we won't have to take you through those steps. Jupyter Notebooks. One of the reasons we like to use them is it can use multiple programming languages, including R and Python. And the Jupyter Notebook on Research Desktop has the kernel for both. It allows for detailed annotation of code. So you can see some examples here of how detailed it is. So you can really explain what's happening, which makes it a great pedagogical tool. And for beginners to learn how to code. But we also have a department that have PhDs in computer science that use Jupyter Notebooks to do their coding in. So it's powerful enough for experts as well. The programming language Python, I'm going to give you a brief overview, was created by Guido van Rossum and first released in 1991. So it might be older than a few of you in here. It's named after Monty Python, the traveling comedy, the comedy troupe, not the snake, even though that is the emphasis. It's beginner friendly. A lot of times it reads almost like English in a lot of ways. So if you've never coded before, you can go in and sometimes still get an idea of what the code is doing. Not always, but It's versatile. It's used for text analysis, data mining, and visualization, machine learning, or topic modeling, which technically falls under machine learning a little bit. So, and it makes use of packages. So people have already pre-created code that does specific things that helps you out, so you don't have to reinvent the wheel and keep writing that out. So you're going to see a bunch of packages that we're going to be using today. And Katie is going to take over now.
All right, so first we're just going to make sure that everyone is set up to use Red so that they're ready to go when we get to the hands-on part of the workshop. So if you've not already, open a browser and go to red.uits.iu.edu. You'll then log in with your IU credentials, your normal passphrase and username. Then you'll be prompted for Duo authentication. Most folks are right there. One thing, Duo does help with that, because once I see the point where everyone's like poking their phone, then I know that everyone's gotten to the Duo stage of authentication. So the next step, we are going to download the Git repository, which is going to have all of the scripts, notebooks, and data set that we're going to work with today. So inside Research Desktop, open Firefox, which you can see either on your desktop or up in the top of the browser. And then navigate to github.com/cyberdh/text analysis. And those of you who were last week will need to do this step again because we've made some updates to the repo for this week. All right. Everyone in a good spot? If I don't stand in front of the link. All right, how are things going? Okay. You're good. Oh, are you trying to if you're trying to copy and paste from your machine to, you're on two different computers technically. Yes. So unless you have the slides open in Research Desktop, you won't be able to copy paste. Sorry. Yeah, it's hard to get your brain sometimes around the fact that it's not the same system, and so it doesn't know what you saved in your copy memory. All right. So next, we're going to download the repo. So click clone or download, and then choose download zip. You'll then get a new window after that, and you want to pick open with Archive Manager, that first option. Okay. And so when you click OK, yeah, a new window will open and you'll see the zip. So select the zip in the new window and then choose Extract. You want to extract the files to your home Carbonate directory. So make sure that's selected and then click Extract again. Oh. I'm not sure.
It is
yeah. All right. Click Extract. Oh, yeah, you can, yeah, close is fine. We don't need to go into the repository. All right. Make sure we're all on the same page. Does everyone have the repository downloaded now? Okay. All right. So those of you that were here last week that already have dot modules, you don't have to do this step again. For everyone else, first we're going to create a file called dot modules, which makes sure that the correct version of Python is loaded in when we run the notebooks. So go to Applications, Utilities, Text Editor in red. We're going to make a new text document. Once you have that open, we're going to type these 2 lines. First line, module unload Python, and then a new line, module load Anaconda / Python 3.6 / 4.3.1. And when you have that typed, you'll click save and then name the file dot modules. And then make sure that's in your Carbonet home directory, the same place you put the text analysis zip, and then choose save. Just in your home directory, yeah. Yeah. If you've already done it, then you don't need to do it again. You were working on your desktop. Mm-hmm. Okay, everyone good? Matt, is everyone online good? All right. Okay. We are going to add next 1 line to an existing file. So go and open your home directory. You'll see name home on your research desktop. So double click that and your home directory will open. Then go to view show hidden files. Because all the files that start with a dot are hidden. So we have to see them before we can edit them. So then scroll down until you find a file called .bashrc. Has everyone found that? Once you have that file open, double click, it should open in a text editor inside red. You have scroll down until you find the line that says user specific aliases and functions. And then we're going to add this text at the bottom of the slide there. Export space and then Python #seed = 0, and make sure that you enter it exactly as it is given here with those spaces and capital.
We do this because the topic modeling is probabilistic. So Python runs a different thread when you run it. So you're going to get different results in your topic modeling every time you run it. This keeps it stable. This keeps you on the same Python thread. And then later in the code, we'll also be setting the seed as well. So this all allows you to have reproducible results later.
All right, is everyone set? So once you've added that line, click save, and then you can close that text document. Everyone good? All right. Now to get the dot modules and .bashrc files in effect, we need to start a new session. And so click the red log out icon on your desktop, and this will start a new session. The green disconnect then link button suspends your session, so everything stays the same when you log back in, but this time we do want a new session. So log out, log back in, and once everyone's been able to do that, we will launch Jupyter Notebooks. Is everyone back in Research Desktop? Okay, it's loading now. All right. Once Red is back up, you're gonna go to Applications, Analytics, and then choose Jupyter Notebook. Click that, and it may take a few seconds, but then Jupyter Notebooks will open in Firefox. Everyone looking good? All right, so now we'll be all set when we get to the workshop part, but first, David is going to take you all through an overview of topic modeling.
And now for something completely different. All right, so what is topic modeling? Topic modeling is described, at least by the people who made Mallet at the University of Massachusetts. Topic models provide a simple way to analyze large volumes of unlabeled text. A topic consists of a cluster of words that frequently occur together. Using contextual clues, topic models can connect words with similar meanings and distinguish between uses of words with multiple meanings. So we're going to give you a little vocabulary. So we're going to go over today latent semantic analysis and LDA, latent Dirichlet allocation. If we have time, we're going to do the word embeddings, but we're going to save those for last and see. The latent semantic analysis basically compresses using this single value decomposition down here to condense a term document matrix. And this is what we're going to use to find document similarities. So we're going to use Shakespeare's plays and see which of his plays are most similar to the other plays. Latent Dirichlet allocation, we're just going to call that LDA, so I don't have to say Dirichlet all the time. We're going to go into a little analogy later for that because it's kind of hard to explain otherwise. But again, it is probabilistic, so it uses probabilities to determine topics within a text. And then word embeddings kind of do the opposite of other topic models because they look at the word level. So you're basically going to look for you usually come in with a word of interest and you try to see what other words are similar in meaning or have similar relationships. So, as I said, we were going to get into a nice little analogy. So imagine that there is a farmer's market on the other side of town, okay? And you've heard people rant and rave about this farmer's market. Before you go all the way across town, though, you kind of want to know what they actually have and if it's worth going. So one Saturday morning, your neighbors leave for the market with empty baskets, and they all return with full baskets. You assume that your neighbors can only choose from the types of produce available at the farmer's market, and that there's a limited variety of produce available. So it's not infinite. There's only so much that there can be. And since it happens to be late summer in our fictional story, and Katie pointed out to me that some of these don't fit for late summer anyway, but again, it's a fictional story. And one by one, as your neighbors return, you start to look at the contents of their baskets. And looking in, you start revising your predictions. Again, it's probabilistic, you're predicting. You're trying to determine the probability that certain things go together. You reconsider based on which produce appears together in a basket the most frequently, how to reorganize the 10 produce types. So you've determined there are 10 types. And examining all of the quantities of produce in each basket, you begin to predict not only the range of the produce that might have been at the farmer's market, but also the relative quantities. And over the course of sampling your neighbors, coming to the conclusion that the selection of produce at the farmer's market consists of the following: about 20% green apples, 20% red apples, 15% pears, 10% winter squash, 10% cantaloupe, 5% corn, beans, tomatoes, and then a miscellaneous section for the stuff that just doesn't fit anywhere. So as more neighbors arrive, you can adjust this as more and more produce comes. And if you want to get this story in full, there is a Journal of Digital Humanities article where I borrowed a large portion of this. So let's see what that actually has to do with LDA. LDA assumes documents are like the neighbors' baskets, okay? Neighbors are like authors who select from a limited number of available types of words. Each author neighbor, chooses how much of each kind of topic or produce they use for each document. So most LDA things you go into are going to ask you to choose how many topics you want. You choose that ahead of time, and it's kind of arbitrary. I mean, it's a number a lot of times you play with to see what you get and what looks to be a good number of topics to choose from. There's also ways called coherence that will try to do that for you. But again, you're kind of having a computer tell you what number of topics seems to produce the best probabilities of groups of words. So, and our notebooks do have the ability to do that, but for today, when you see it, they'll be turned off because it also takes a long time because they're basically running LDA for every number of topics possible that you give it. So if I want to try it on 10, 20, 30, 40, 50, and 60 topics, it's going to run it that many times on try each of those topic numbers and see what we get. So real LDA, though, remember, does not label the topics for you, though, and it does not understand what words mean. So to go back to our example, imagine, in our example, you come across a fruit you did not recognize. Say it's an Asian pear in a basket of apples and pears. How would you determine what topic it went with? You have no idea what this is. You've never seen this fruit before. So same as a computer when it's looking, it doesn't know what the word is. It doesn't really know that these things, as a human does, go together, right? So you would see what it was often paired with. Huh? Yeah, that's right. Some puns today, yeah, all right. All right, trying to keep it light. And then you determine the probability that it is a pair, okay? So that's a very simplified way of explaining LDA. Now, for LSA, we're going to look at green eggs and ham. So a little Dr. Seuss for you. So LSA does something and uses something called vector space. So it's basically turning words, or in this case, documents, into a vector set of numbers that can be plotted and graphed. And so the vector space is defined in the terms of the vocabulary. Each and every word in the vocabulary has its own distinct orthogonal dimension. So that's a right angle dimension. So for example, if our corpus is green eggs and ham, then after we do our text cleaning, which most of you I think know is when you lowercase everything, move stop words, stemming, or today we're actually going to use lemmatization because we feel it's better. I'm sure there's arguments for that, but we're not going to get into those. Our vocabulary is left with boat, box, car, dark, eat, egg, fox, goat. And there ends up being about 17 words or dimensions, each relating to one of these terms. So if our documents are sentences in the story, so imagine each sentence is its own document now, okay? Each of them will be described by a 17-dimensional vector, so a list of 17 numbers, and every time a word appears, that number is going to go up. So then that means each sentence is going to have its own numerical value, its own vector value. Okay, so it's the same with a document if you're doing this. Notice that this methodology implicitly assumes that the 17 words in the vocabulary are orthogonal to one another, which best describes a situation where the presence of a given word in a document is independent from the presence of the other words in the vocabulary. So it's not necessarily looking at where they are in relation to one another. So in practice, in the case of green eggs and ham, I expect we'd find that green egg and ham co-appear to a large degree in the documents, or sentences in this case. So again, with our vector space defined, we now need a method by which we can determine each document's position along each of the axes. So recall that each axis represents a specific word in the vocabulary. So for each document, we only find a way of giving it a score for each word in the vocabulary. So for example, take, I do not like green eggs and ham. That's one of our documents or sentences, okay? After making everything lowercase again, stop words, lemmatizing, stemming, we're left with green egg ham. Basically, that's the sentence now. It's been reduced to that. Counting the number of occurrences, that sentence now has this embedding because we know there's 17 words. And so you can see and it's in alphabetical order. So you can see green egg ham. Or I guess in alphabetical order would be egg, green ham, sorry. And then taking the dimensions and that, yeah. So similarly, the line eat them, here they are becomes eat, eat. And so you can see there's only a 2 where eat is, because we have it occurring twice. So that now becomes the identifier for that document. Okay, so that's just a basic run over what's kind of a little bit of what's happening in LSA. Again, there are whole papers written on these things, so trying to explain them in a short time. Word embeddings. Sorry, I thought I heard somebody yelling out there. So the question that a word embedding model asks is, what if we could model all relationships between words as spatial ones? So this is similar to LSA. It's going to use word vectors again, except instead of comparing documents, it's going to compare it at the word level. Or put another way, how can we reduce words into a field where they are purely defined by their relations? So such a space allows us to think in terms of similarity. What words are like other words? How can we learn from these relations, and how does unexpected closeness extend our understanding of a field? So word embedding models try to reflect similarities in usage between words as distances in space. Example, you'll get a cosine similarity using our thing that shows that man and woman has a cosine similarity of 0.547. Some of these numbers, I always tell people, they're important, but in some ways they're kind of arbitrary because you're really looking at it in relation to the whole. So if you see that in some cases 0.547 in some documents might be really high and some it might be really low. So to determine if in that document that is actually showing a relationship for that document, you have to kind of know what else is going on there. Word embedding models also try to reflect similar relationships between words with similar paths in space. So this is where a word embedding can actually do analogies. So because you're kind of like adding and subtracting different vectors, it's going to then measure what the distance is equal to these other words. So you can actually put in something where it's the vector king and vector for woman minus the vector for man equals the vector for queen. So basically it's telling you man is to king as woman is to queen, and you can actually do that with a word embedding model. So topic modeling, what is it good for? And Katie is going to tell you that.
The next slide has some high-res images, and so it takes a second. Or 5. Oh, here, okay, we got it. All right, so this is an example from LDA, making word clouds from topic models based on the text of Shakespeare's plays. And the text of the plays that we're using for this are cleaned versions that we've gotten from Folger's Shakespeare Library. And as David mentioned, clean means punctuation removed, lowercase in the processing. It also means that since these are plays, the stage directions and the character identifiers have all been removed, so we don't have each time a character speaks their name appearing, because that kind of throws off your results. All right, so the first one is our kind of family topic. And again, the system doesn't tell you what each one is. You can kind of look at what it's come out with and figure it out for yourself. And so we have home, wife, master, house, all showing up with a really high weight within this word cloud. The one in the middle is our love topic. So we have love, lady, fair, heart. Sometimes I think that the system is being funny on purpose because hate is right inside the H that forms heart. I really enjoy how it turns out in the organization here. But also we have night, which comes up a lot with like romantic stories. I think Romeo and Juliet. And for something very different, we have familial relations was what we kind of decided this one was. It's kind of got the whole range of things that you can have happen within family relationships. Blood, wound, bear, strike, shame. We seem to be a little on the negative side here. Familial conflict, right? Sorry, the first one was more relationships. Yes, and so if you're familiar with some of Shakespeare's plays, you're probably can see where a lot of these are coming from. Think Hamlet. We see a lot of familial violence within Shakespeare's works. So it's not surprising that that's one of the topics that came up. And if you're like, you think of Macbeth, Blood in Hand, that's really big topic within that play. And so it's not surprising to see it show up here. All right, slightly less bloody. We've got LSA with heat maps. This is also looking at Shakespeare's plays, but instead of looking at topics, it's doing document similarity comparison based on comparing each of the plays to all of the other plays. The output is a matrix, which shows how each play compares to all of the others. The heat map is colored based on cosine similarities, like David was talking about, which is a numerical index of how similar each of these plays is to the others. And in this case, you can see that we've got a lot of similarities where we have quite a bit of the green. And then we have this one here that really stands out as being distinctly different from the others, which is Julius Caesar. And so we thought about this a bit to see why this would be. And there's a couple ways that this is different. It is a tragic history, so it's not just a tragedy or one of his history plays, so it has a bit of a genre difference there. It also doesn't have much comedy in it at all. We don't see a lot of lewdness or comic characters, which even in the other tragedies we do have in Shakespeare's plays. Think of Othello. Iago is very vulgar in things that he says. We typically have a pair of comic characters even in the tragedies, but Julius Caesar really does not have that. And so that's why we see this one really standing out in the way that it does within this matrix. And then an example of Word2Vec, we've got, again, this was running on all of Shakespeare's plays. This is a table showing the cosine scores for words related to woman. And we see man to the top, then wife, lady, heart. We start out pretty good. Gentlewoman, honest, truly, love. Then we get foolish and appetite. And then here we've got a word cloud that shows the top 200 words. And so this is taking those cosine scores, but representing them through font size and color. Larger the font, the more heavily weighted the word is, then the colors reflect words that are weighted about the same. And so we see, wife, lady, man is one of the largest ones. Married comes up, but is much less heavy a weight as the ones that we have in the center. Daughter, honest, faith, so we have kind of a mix of things that would be positive and negative here. And so topic modeling is useful for a lot of different cases. We have large corpora where it's very useful for looking at all the contents of all of Shakespeare's plays. You can also apply it to a single document to look at relationships of different parts or at sentence level. So you can use it for smaller corpora when you're looking for differences in words usage. You can also use it to weed out documents or show which have significance. So the example with Shakespeare, it's like, oh, okay, there's something very different about Caesar, and then you can go look at it more closely with close reading and see what is causing that difference. You can look at transit topics over time. The heat matrix includes the dates that each of those plays were written. And so you can bring in a chronological component and see how similarities and differences being tracked over time with Shakespeare's plays. And then with Word2Vec, you can look at word level and study how word is being used within documents. Any questions before we move on to the notebooks? No? I'll look pretty good. All right, so let's make topic models.
All right, so open the, there you go, Chrome. All right, so our notebooks actually for the topic modeling are actually broken into two. In the case of the topic, the LDA, it's actually into three. One of them is for cleaning your data. So that's basically produce for you at the end your LDA model. Part of this is to help, there's two reasons for this. One is because it is probabilistic, if you get results you like and don't want to mess with them and have to rerun the notebook and possibly change those results, then this allows you to do that. You can run it, you can see the results you like, and it saves the model and all of that in a separate folder. And then the other one is the one that's going to get you your, we have two versions. One gets you the bar graphs that show your topics and then the weights of the words in those topics, and then the other one is the word cloud that we showed the example of earlier. But this way you don't have to worry about that. The other is for time, because again, you don't have to run it all, and if you have a very large corpus, LDA can take a long time even on the supercomputer to run. This way you've already done kind of the hard computing part, and then if you want to go over and you're just wanting to make changes to the output, the graphical, like the word clouds and the bar graphs, you can do that without having to rerun everything. So in Jupyter Notebooks, there are three ways that I like to run the code on here. So the first, if you're really just wanting to run the whole thing from the get-go, you can go up to Cell and you click Run All, and that will just go through and it'll start at the top and run the code all the way down to the bottom. The other option is you highlight this cell you want. So in this case here, I'll highlight the first one, and you can just come up and click the play button up there. The other way, which is actually my favorite, is if you just hit Shift Return, so Shift and then Return, it will go through everything, including the annotations. It'll just run through them. And since it's not code, it just skips over them. Then it'll run the code cell and then it'll skip, and you can just kind of keep skipping that way. This is helpful because sometimes you make changes and you want to go back up to a line of code and just run that line again and see what happens, make sure it works, especially if you get an error. But now we're going to go through, and as you can see, the highlighted parts in red are where I'm probably going to stop and talk a bit more. But other than that, I'm going to try and go through as quickly as I can so we have time for the LSA, hopefully the word embedding, and some questions at the end. So this first one is actually reading in our Python environment. So we have all of the packages you're going to need for our notebooks saved in a Python environment on Red. So in order to have access to that, you need to actually run that first line of code. If you're running it on your own computer, you'll want to comment these two lines out, but you still want to import those two packages. We come down here, and this is where we're importing packages. So you can see all the packages that we need in order to do topic modeling. And again, there's more explanation above about what they do and more about Python packages and all of that. Now, here's another important one where you may want to make some changes, not right now, because this is all pointing to what we need for today. But this is basically just file paths that are pointing to where our data is, where we want data to be stored afterwards and all that, so we can call it back with these variables later. So you'll want to change your paths if you have your own data that you're using again later to whatever the folders and places are that you have that data stored in, whatever folders you want it stored in. So. And now we're going to set a whole bunch of different variables that we are going to use later. And you can see there's a lot of explanation. So I'm going to go over some of the important ones. The source, this is where you're going to say whether you want, if you want a file by name, then you'll change that asterisk up there to whatever the file name is. So if we were doing Hamlet, I would write Hamlet in there instead. This is basically saying I want everything. It's a regular expression that kind of means all. So it's basically saying I want everything, and then this dot text gets appended. So it's basically going to tell you I want everything in this directory that ends as a dot text file. So you can change that because this does later on have the ability, people like to do topic modeling on like tweets and social media. So you can change it to either .csv or .json if that's your choice, if you're wanting to do Twitter, and we can go into that in a bit more detail later too. Doc level, this is basically saying that do you want to read an entire directory? If so, make that true. If you just file, then set it to false. The 100 is actually only going to be used later on if doc level is false, because we're basically saying we're chunking our one document then by 100 lines. So each 100 lines becomes its own document, because you need to have those documents in order for topic modeling to really work properly. So we have it set as a default 100, but again, that's going to depend on your data and how big it is. So the next part is setting our stop words. We're going to use the NLTK packages stop words list. So we're setting it to also have a way to read in your own custom stop word list, which we are actually going to use because we have one from the Folger Shakespeare library that has early modern stop words. So that are, you know, it's fitting for Shakespeare's plays. It gets rid of like the these and thous and all of that. So spacey limitizer. So this is saying we want to use lemmatization. We're using the spacey package for that. You can set that to false because some people want to see all of the endings. So what lemmatization does is it basically breaks words down. It has its own dictionary and way of determining whether a certain word can get broken down to a root term. So in some cases, people use stemming. Stemming just cuts the ending off, whereas lemmatization actually brings it back to a specific root word. So, so a word like run or running, if stemming would cut off the ing, so then that would leave you with an RUNN, which would be different from run. Whereas lemmatization will actually recognize that running is referring to run and will make it RUN just like RUN. So that's why we feel like it's better. The other thing is too, if you get things like better and best, it'll actually change it to good because it's all forms of that term. The same with any to be. So is, are will all be changed to be, BE. So it changes it back to that root. Coherence, we set it to false. This is just saying I want to run the coherence scores that we talked about earlier. But again, remember that will make this take a lot longer because you are basically running the LDA repeatedly. But for speed, we've set it to false. Our stop word language is English, same with the lematizer. And there are different options in NLTK for the stop words and in spacey for the lematizer. So you can actually lematize in Spanish and stop words. There's a Spanish list, French, and all that. So the encoding, I think is pretty self-explanatory. Errors equal ignore. That's for the encoding. That way, if you get encoding errors, it's just going to kind of ignore them for now. In some cases, that might be important if you want to change that and actually get the encoding errors so you can solve those problems. If you think that's going to be an issue, you can just change ignore to none with a capital N and without the quotes. Text, that's just for if you have tweets, because Twitter tends to label the actual content of the tweet as text, whether it's in a JSON format, which is the original format tweets come in when you pull from the Twitter API. Or some people then convert them to CSV, and that's why we have that as another option, because we've had a lot of people that got data from somewhere else that had been turned to CSV and they didn't have a way to make it JSON. And then these two things are empty lists. So we have an empty list of stop words and then an empty list called docs, and those are going to get stuff added to them farther down. And then we just have our stop words here. So you can see that we're actually adding some extra words to our stop word list. Would, said, says, also are now going to be added. They weren't included in the NLTK one, and they're not in our custom one. So we're just adding a few extra. And now here we're unzipping our folders. So mallet is already loaded into our GitHub repo. And so this will go in and unzip that and extract it so it can go into the mallet folder and actually run it. So the package that we're using is Gensim, and it has that mallet wrapper. So it can actually use mallet for its LDA, but it also has its own version of LDA that it uses. But we've chosen mallet because people know it and like it and feel more comfortable and warm and fuzzy about it. So, so now we're just reading in our files. So if it was .text, that was up there. Here we're reading in our CSV or JSON if we chose that. And now we're changing all of our terms to the term data. So this is something so that if you're using it on documents or if you're using it on Twitter data, it will now all just be called data. That way you're not having to go down in the code later and try and find where it says docs or where it says tweets instead. It'll just say data for everything. So here we're tokenizing, and this is also using Gensim to lowercase and remove punctuation. And then we're going to actually here then find some bigrams and n-grams. So this is only if they're used a lot. So like if you have the term New York, you want that to be one word in a LDA. You don't want it to be new and York separately because that's going to throw everything off. So if it occurs enough and there's settings, and up above I explain in more detail like what the threshold means and how it's figured out. Minimum count means it has to appear at least 5 times in order for it to even be considered. You can, again, raise and lower that depending on your data. But this way you can see we've got some that met our threshold. Poor Tom, foul fiend, 100 nights. So alack, alack. So we'll see. And some of these we haven't cleaned the stop words out yet. So that's why you're seeing some things that look like potential stop words that are still in there. So and then here we're creating our functions that remove the stop words and make the bigrams and trigrams and do the lemmatization. Functions don't actually do anything right now. As you're declaring it, it's just there. So now you're just saying this function now exists. So it's not actually doing anything except storing that function in memory, because now we're going to pull these functions down here and actually use them. So after this step, you will have, it will be lemmatized, stop words will be removed, and the bigrams and trigrams will be included as part of the text. So you can even see down here, foul fiend is still there and all that. So now we're going, if we lemmatized, we're going to create our corpus that is going to be used in mallet. And this here is just a test. We just want to see, okay, in our dictionary, what is the 10th term? It's abuse. And then here you can actually get the words and the counts. And now we're going to actually use mallet. And here we have our variables that are very important. So we have the number of topics. We decided to go with 20. Again, that can be adjusted. And it usually is, depending on your data and what you're wanting to do. The number of workers we have set to 1. This is important for reproducibility. If you set it to 2, that means it's for parallelization. It will be faster, but it also means it's going to be doing, it's almost like having 2 separate people sorting our fruit baskets earlier, which means you're going to get some different results every time you run it because you're having 2 separate processes happening at the same time. So you want to keep that to 1 for reproducibility. If you're more interested in speed and don't care if other people can reproduce your results, then you can set it to 2 or 3. The number of iterations is how many times it's going through this process, because every time it goes over it, it determines, okay, no, I'm going to move this back over here. I'm going to move this here. I'm going to try this here. And it keeps doing it. And that's how it gets that percentage probability that these words belong together and these words belong together. So it kind of keeps refining as it goes. And then the seed, again, is for reproducibility. So that you're just saying, I want this thread. I want this one here, and that's the one we're going to use repeatedly over and over again. Otherwise, that's a random number. And so again, you'll get different results every time. So now most of this is only if coherence is true, although this one does print out. This just gives us 3 of our example topics or groups of words. And again, these are weight. It's weighted. So this doesn't have anything to do with frequency or how often this occurs. It's how important that word is to this topic. And so all of this is for coherence. Like I said, we didn't do it. It takes a while. And you know, keep going. If you wanted to hit run, it might still be going, and that's actually okay. And take a while to run because it is doing some pretty intensive math here. And so now the last part, this is where we're going to export everything into that folder so that then we can go into the results one and run that and actually get some results, which I'm going to go over with you now. I'm just showing you the bar graph one for today. So the other one does the word clouds. But since we already showed you some examples of the word clouds, I figured now would be a good time to do bar graphs. Same, again, calling in our Python environment, pulling in packages, file paths like last time, setting a couple variables this time, and make sure this matches, this doc level equals, because remember the other one had it. If that's false and the other one was true, it'll still run, but some of your results are going to look a little weird, like you're not going to get the actual play name, the file name, in some of the tables, which you're going to see here in a minute. So now we're loading the data that we just saved in our previous notebook. And we have to create the corpus again based on that. And so now we're creating a function that's going to help us for all of these. So here you can see our first one. This is telling us that King Lear, the dominant topic for King Lear is topic 7. And that it was about 17% of the topics, or of the text, was that topic in King Lear. And the topic is Lord, man, fortune, friend, fool, nature, noble. And you can go on down. And then we get another table, and all of these are outputted. You can see here where it says chunk rep CSV. That's going to be a CSV file. So it's going to output this as a table that you can then mess with in Excel and do whatever you want to it and look at some of these results and numbers in more detail. But right now we're just outputting it so you can kind of see it. So now this one is going to go through, and it's actually going from topic 0 all the way to topic 20. So remember, Python starts counting at 0. That's another thing. It starts at 0. So that's why it says topic 0 and then it ends at 19. We still have 20 topics. It's just Python is different in that. So if you've been doing R before, R starts at 1. So it would be 1 through 20. But so you can see our topic is 0, and it's telling us that Titus Andronicus is the file that best represents that topic. So that's the play. And it was represented in almost a quarter of it. Over a quarter of the play is about this topic, which, again, remember, you see Romeo. There's no Romeo there. But it's because we have 36 plays and 20 topics. So it's going to combine some of these plays into one topic. So when you do the rest of these, between Romeo and Juliet and Titus Andronicus, they actually match up really well. But then there's a few where each of them's a little low in one of those words in the topic. So this might be something where, one, it either tells us something, who would have thought Titus Andronicus and Romeo and Juliet actually had similar topics, or it tells us maybe if I don't believe that I need to go back and check my topic numbers. This one is going to tell us topic distribution. So how many times was topic 0 the dominant topic? Well, only once. But topic 1 was the dominant topic 3 times out of our 36 plays. So this way you get an idea then for which topic in our entire corpus, which one does Shakespeare repeat a lot? And so you can see we only get 3 as the highest number here. But it happens a few times. So topic 1, topic 3, I believe topic 12, and then topic 18 seem to be ones that he liked to rehash again. And then we get one nice little stacked graph that just goes through. I picked topic 0 for it to order it by. So you can see Titus Andronicus, Romeo and Juliet, and this way you can go through if you're interested in a specific topic to see which plays. But then you also see the other topics and which ones are more prevalent. So you can go back up and see, so like Romeo and Juliet, oh, topic 11 is actually the most dominant topic in that one. I'm gonna go back up and see what topic 11 was, if you wanna do that. And then finally, our bar graph, which shows all 20 topics, and then you see the bar represents the weight of the word in that topic. And this is also outputted in an output file for you, so you can, as a PNG, so you can bring it in, put it in a slideshow or something like that. And now Katie's going to talk to you about LSA.
All right, so the LSA notebooks are also divided in between a cleaning notebook and a results notebook. We've got a quick outline of those here, like we did for the LDA. So for LSA, we go through the same basic steps, which is if you walk through this notebook, you can see we go through and set up the same environment, import packages, read in the data set. And again, if you were running this on your own data, this is where you would point to your own path for your data set. We have the similar variables here. You can turn stop words on and off. You can also turn limmatizing and lowercase on and off as well. And there are some cases where you might not want these things to happen. I know in my research, I run analysis on melodies that are alphanumeric strings. And I use this notebook for that. And so I don't want to lematize because my pitch groups are not in the lemmatizing dictionary. And there's capitalization that's significant in my corpus because a capital letter means something different. So I turn both of those to false when I'm running analysis on those. And so depending on your data, you make changes here. Same for stop words. You can use them or modify them as you needed to fit your corpus. We'll bring in our functions, our documents. And then here's an example of what the output's going to look like. We get our cosine, our rate of appearance for each of the terms that are showing up. This just gives you a little excerpt of what the big table is of how it's showing how frequently each of these terms appears in each of these documents.
This is term frequency. This is term frequency and inverse document frequency. So TF-IDF. So basically, what that does is instead of just using plain counts, it's actually going to also take into account word appears a lot in one document. So it's still going to give that some weight. Whereas before it wouldn't. It would just say, oh, so it only appears this many times, and that's it. So that's why it's in decimals instead of whole numbers.
All right, and so then just like the other cleaning notebook, it outputs as a .csv, which you can then look at to see how your data has output. And this shows, like that matrix, all of your documents compared to all of their documents with a cosine similarity score for each. The heat map then takes your output, runs the same processes for importing and packages as we looked at before, but now we have an excerpt of the matrix itself, looking at the cosine similarity scores to show you how similar each of these are. You can see it's NA in the center where the play is being compared to itself, since obviously that would be a score of 1 because they would be exactly identical. And then the notebook will output that for you, so you can look at that output as well. And then it actually plots the heat map for you and exports it as a .svg. You can change some of the settings here, obviously the file name, the DPI, depending on the kind of resolution that you need. You can also change the color scheme, font scale to suit your needs. And so here we've got the same heat map that we looked at earlier, comparing all of Shakespeare's plays. And again, you can see this has come out exactly the same as the other one did. We've got a lot of green with the really noticeable line of red with Julius Caesar. All right, are there any questions? If you're online, you can type your questions into the chat and Matt will pass those on to us.
And we don't have time for the word effect, so if you want me to show you that to you, we can either I can talk with you a little bit afterwards, or you can set up a consultation and we can meet with you and run through that if you have a project for that as well. Do we have a question on there? No? Yeah, if anybody's listening online, you can type your questions in too. Again, these are free for you guys to use, so go back in. Oh, these are free for you guys too, so you can go back in too and download them and use them at your leisure. And if you have problems, you can always email us then too. Actually, let me put up our final slide here. Sorry, so you can get some information. And we'll just. There we go. So our contact is cyberdh@iu.edu. Again, the slides for today are available at this link. And information on previous and current seminars is that go.iu.edu/24xc. So that will actually have the recordings and stuff too. So I don't know if last week's is up yet, but you can listen to it then instead of just looking at the slides. Oh, because she said it usually takes a few weeks, sorry. Katie's our expert on the Zooming recording process for all this stuff, so. And other things, not just that. Lots of other things. Doctorate in Zoom. And musicology, they go together. Somehow. All right, well, thank you all for coming, and hopefully we'll see a lot of you next week at the sentiment analysis one. And yeah.